Alrighty, CNT125, we're continuing on Chapter 9. We're on the section now on routers. So just kind of reminding us, homeowner router type of thing, commercial type router. There's a homeowner router over here as well, but commercial type router, or the routers we have in our lab room. You can think of those as commercial routers. The router's job is to join two or more networks and passing traffic from one network to the other one. These could be two Ethernet networks. It could be Ethernet to a WAN provider network. A lot of times it is LAN to WAN. My LAN out to the WAN, or connection to another site kind of thing. This right here, our Ethernet LAN to ISP network, if you will. Sometimes connecting different transmission speeds, even different protocols. So the router has a couple different things it needs to do to make that happen. The routers are responsible for determining the next network to pass packet to forward it onto its destination. Now, I'm reminding you back from, I'm going to say maybe chapter 3 of our book. Remember the job of our router. The routers are going to read the IP addressing, layer 3 IP addressing, to get data to the correct network. And I use the example here of getting it to the Hack York campus as opposed to the Hack Harrisburg campus. So it's like routing. I'm going to go to Hack York over here as opposed to Hack Harrisburg by reading those IP packets. So the router is going to get it to the correct network. Once it gets it to the correct network, it's like, I'm done. Now the switch steps up and says, okay, I got this. I'm going to read the layer 2 addressing, the MAC address, to get it to this computer as opposed to this computer. This computer in the lab room as opposed to this computer in the lab room. Okay, the router is getting it to the correct network. The switch will get it to the correct device. So remember those two pieces as we're working through routers here. That'll help maybe sort some of that out as you start talking what the router is doing. Typically, the router itself has its own processing, operating system, memory, input, output ports, etc. Again, if I were to crack open a router, don't do it, but if I did, I would see these kind of things. It's basically a specialized computer without the video card, without the keyboard, mouse, ports, and those kind of things. And actually, as a side note, you can usually take an older PC, load on a router operating system. It's usually a Linux-based one. Put on a router operating system with a couple network cards in, a couple NICs in, and turn it into a router. It can be done. So just letting you know, it's kind of a specialized computer. As I look at the front, a lot of times I'll see that I have a couple LAN ports, maybe some WAN ports on. Sometimes you only have two router ports, an in and an out. These would be your console ports on the back side. Actually, your console port on the back side. If I look at one of the other routers we have in the lab room, the 4200 or 4300 series routers we have, console port here, here's your LAN ports. These would typically be WAN ports. A router joins two or more networks together. Routers can do these types of things. Connect to similar networks, LAN to WAN, interpret layer 3 and sometimes even layer 4 addressing, port number kind of deal. It's going to determine the best path from A to B and reroute if the first choice is down or broken, and there's another path available. Routers may perform any of the following optional functions. Filter broadcast, that's usually going to happen. Prevent certain types of traffic from getting to a network. This is where the filter or access lists come into play. Support simultaneous local and remote connections. Yep. You can actually have a remote connection into it. Provide high network fault tolerance. Yes, especially if I have redundant components and redundant paths. Monitor network traffic. We're going to do that later this semester. We're going to do some network monitoring with this. And even diagnose internal or connectivity problems and triggers alarm. Again, we're going to do this later in the semester as well. Have it do some network management for us. There are different types of routers. There are core, edge, and external routers. Core routers, interior routers, direct data between networks within the same autonomous system. Autonomous system, a group of networks operated by the same organization. So you could think of, Hack as an autonomous system and the networks inside, maybe going between these buildings and those buildings. All that is under one, under the control of one company, one organization. So that would be like an autonomous system. And these core routers in here or interior routers are moving traffic among them. Edge routers or border routers connect this company or this site out to the ISP or another site. Exterior routers refer to any router outside the organization that's basically routing traffic between different autonomous systems. These are usually ISP or backbone type routers, just to give you an idea. Here is some examples of those. I took the picture they had and I kind of broke it out for you. This would be core routers inside of our company managing the same autonomous system. Edge routers would be connecting our company, our site, out to ISP or potentially another site. That'd be your edge router or border routers. Some places that's the only time you do have a router. Some instances that might be the only place you actually do have a router, that edge router. And exterior routers, these would be ones typically run by your ISP. Homeowner routers, a lot of times are kind of plug and go. You don't usually need to do too much. Your commercial multi-protocol routers usually need configuration to configure them and get them up and running. As we noticed in Chapter 8 when we did the Subnet Application Lab, we had to console in and put some interface addresses on and some routing protocol information on just to get it running. And we have this kind of configuration that we're dealing with. Now, the router is going to start building a routing table, and it's going to do that with a routing protocol. We'll get to that in a minute, but it's going to be building a routing table. The routing table is kind of like your mental map, this right here. A mental map of how am I going to get to work. Let's just say you're just trying to drive to work. Well, you have a mental map of like, okay, when I go to work, I'm going to go to this route, this pathway. But then you also know, hey, on blah day it's extra trafficy, or blah time it's extra traffic. I don't go that way. I sit in traffic the whole time. I will go this other way over here. Well, you're building a routing table, a mental map in your brain. Routers are going to do the same thing, but they're going to do it just based on the network, what network I'm trying to reach, and how am I going to get there. And it maintains that in a little table of what network and how do I get there. And it's learning that and maintaining that. And it looks something as simple as this. It learns the networks. You notice there's no hosted portion there, just the network portion. And it says, okay, this network, I can get there via this port. This network, I can get there via this port. This network, if I go out this port, I will be like one router away, and then I can get there. That's what I'm seeing here. These are some things we're going to look at in a minute. So it's maintaining that kind of table of what network and how do I get there. Routing paths are determined by one of the two following ways, either a static route or a dynamic route. A static route is something that gets configured in by a network administrator. These do occur. These do happen. A static route between maybe a small business and the ISP. If there's only one pathway there, why do I have to have the router keep learning that same pathway all the time? I would just code it in saying, this is the way to get there. Done. Meanwhile, a dynamic route is something that the router learns and calculates. It learns that network's there, it calculates the pathway there, and it maintains that. And it's there as a choice one, and if that fails, it then tries to learn another way to that network, and there might be another way to that network. You know, think about HACS campuses, you know, Lancaster, Lebanon, York, so forth. There might be one main path to Lancaster, but if that path breaks, the traffic might go to York and then over to Lancaster. That might be the backup route. And dynamic routing would be that kind of thing. It's learning it, it's maintaining it, putting in the table in there, and maintains that until something were to break. So if I take a look at some routing tables now, when I start seeing things like C, that's directly connected. That is a network directly connected to the router, so it knows exactly where it is. Meanwhile, something that has like an S next to it is a static route. It's like, hey, to get there, you go here. To get there, you go here. Okay, that's what we're seeing with a static route. It's coded in. Meanwhile, something that would be a dynamic route, again, we have another C directly connected, but this guy O right here is OSPF. OSPF, that's a routing protocol. It learned that dynamically, and it has that pathway in there to get to that destination. That learned that dynamically and would update that if something were to change. There is commands to see routing tables, the route utility, if you will, the route command, if you will. Well, depending on what system you're on, if I'm on a Linux or Unix system, if I use the route command, it'll show the routing table, the routing path, if you will. Here would be the Linux version here, route. Okay. If I'm on a Windows, I would do a route print, and again, that would show the routing table here, if you will. If I'm on something like a Cisco router or device like so, I would do show IP route, show the IP routing table, and I get something like so. We've done this a little bit, and as we do our Chapter 9 lab on routing protocols, we are going to do this a whole bunch. So this will get a little bit more familiar as time goes on. So how does the routing protocol update the router in its routing table and maintain these paths? Well, it's going to use routing metrics. And again, we kind of know this already. If I'm going to drive from A to B, maybe get to work, I have some routing metrics in my head. And some of those have to do with like how many lights am I going through, how much traffic am I sitting in, how much latency, if you will, how much traffic am I sitting in, versus this way over here. This I might actually pay toll to get there. I get there quicker, but I pay toll. These are all little metrics you have in your brain to make decisions on the way you would drive. The same thing is true in networks. There are things like hop count. How many routers away is it is? Theoretically, the more routers, the further away it is, the longer it's going to take, kind of thing. Theoretical bandwidth, delay or latency on a path, the load on a path. Maximum transmission unit, in other words, how much data can I send on that? Routing cost, which would be factored in by an admin of like, it's an admin level cost. Maybe this link actually costs a lot of money to use, so we only use it as a backup kind of thing. Reliability of a path, topology of the network, all these could get factored in. Different routing protocols are going to use some or a combination of these. And they'll factor those together and say, okay, this is the best path. This is the one I'm going to maintain in my routing table. And again, that is all done with routing protocols. Routing protocols are going to communicate or find this information, update that, and put it into the routing table on the router. The routing protocols are going to build a routing table. The routing protocols are going to communicate in the network and build a routing table. This is like you listening to maybe traffic, maybe on the radio you listen for a traffic update, or you pull up your phone and pull up, Google Maps and look at the traffic on a route to know, am I going to go this way? Oh, that's all orange and red. I'm not going to go this way, so I'm going to go this other path over here. These routing protocols are going to be doing that kind of stuff like you just did to figure out how you're getting to a job site or whatever. It's going to factor those things in, say this is the best path, and put it in the routing table. And the routing table is kind of like the path in your brain of like, hey, this is the way I'm going to drive now. Today, because they're working on that road over there, I'm going to go this way. They're done working that road, I'm going to go on that road that they were working on yesterday because that is the better path, kind of thing. Okay, that's the kind of thing you're going to do. Routers are doing the same type of thing. Well, there's a couple terms they bring out when they start talking about these routing protocols. Administrative distance, convergence time, and overhead. Okay. The administrative distance is a number that ranges from 0 to 255. And that is a number that indicates kind of like the quality of the information, the reliability of the information. If it's a number of 0, that information is excellent. Maybe it's directly connected. There's no better information of like this information to this path is outstanding. Other routing protocols that get used assign an administrative distance to tell you how good that information is. And some routing protocols that are kind of meh are going to have numbers in the 120 range, which is kind of like 0 to 255. Other ones will be a little bit better, so it'll be like 110, that sort of thing, to let you know that's better information. Convergence time, how long it's going to take all the routers to know the same information, whether a network is broken or a network has come online. That's convergence time. Some protocols are going to take a while. They take minutes to relay that information. Others learn it within seconds. And then last but not least, overhead. How much traffic is the routing protocol putting on the network to do all this? If it puts a lot of traffic on the network to do this, it's adding a lot of overhead. It's adding a burden on the network to get this routing information. Okay, when we come back, we're going to continue talking routing protocols.